Right now, as you watch this video, Earth is hurtling through space at 67,000 miles per hour. Our solar system races around the Milky Way at 514,000 miles per hour. And yet, we are trapped. Absolutely, completely, impossibly trapped within the gravitational prison of our sun. Tonight, I'm going to show you exactly why humanity will never escape our solar system. Not in 100 years, not in 1,000, perhaps not ever. Before we journey into this cosmic impossibility, feel free to settle in. Close your eyes if you wish, and let your mind drift through the vast emptiness we call home. This video is designed for those who want to explore space while gently falling asleep. If you doze off somewhere between Mars and the Oort Cloud, that's perfectly fine. The universe will still be here when you wake. If you enjoy these deep dives into cosmic mysteries, I'd appreciate it if you'd subscribe and like this video. It helps the algorithm find others who share our fascination with the impossible. Let's begin our journey into the prison walls of our solar system. When most people think of our solar system, they picture the Sun, the 8 planets, maybe the asteroid belt, and Neptune at the edge. But that's not where our solar system ends, not even close. Beyond Neptune, beyond the orbit of Pluto, beyond anything you learned in school, lies a vast, cold region of space that extends so far into the darkness that it takes light itself over a year to cross it. This is the Oort Cloud, and this is the true boundary of our cosmic prison. The Oort Cloud is a spherical shell of icy objects that surrounds our solar system like a massive cocoon. It extends approximately 100,000 astronomical units from the Sun. An astronomical unit, or AU, is the distance from Earth to the Sun, about 93 million miles. 100,000 times that distance. Let that settle in your mind for a moment. If you could somehow travel at the speed of a commercial airliner, about 500 miles per hour, it would take you 21 years just to reach the Sun from Earth. To reach the edge of the Oort Cloud at that same speed would take 2 million years. But we've done better than airplanes, haven't we? We've built spacecraft. We've sent robots to the outer planets. We've even sent something beyond our solar system. Or have we? In 1977, NASA launched Voyager 1. At the time, it was the fastest spacecraft ever built. It was designed to visit Jupiter and Saturn, then continue outward, forever, into the cosmic ocean. Voyager 1 is currently traveling at 38,000 miles per hour. That's faster than any human-made object in history. It's been traveling for 46 years, and in 2012, NASA announced that Voyager 1 had finally left the solar system. Except, it hadn't. What Voyager 1 had exited was the heliosphere, the bubble of charged particles that the Sun continuously emits. This bubble extends about 120 astronomical units from the Sun. Voyager 1 had crossed the heliopause. It was now in interstellar space, but it was nowhere near leaving the solar system. The Oort Cloud extends to 100,000 AU. Voyager 1 is currently about 160 AU from the Sun. It will take Voyager 1 approximately 300 years to reach the inner edge of the Oort Cloud, and another 30,000 years to exit the other side. Let me put this in perspective with a scale model. Imagine you shrink the entire solar system down. You make the Sun the size of a period at the end of a sentence. On this scale, Earth would be a microscopic speck, invisible to the naked eye, about 1 inch away. Jupiter would be a tiny grain of sand, about 5 inches away. Neptune, the outermost planet, would be about 30 inches away, 2.5 feet. The Oort Cloud, 1 mile away. Our solar system is not a small neighborhood of planets orbiting close to the Sun. It is a vast, cold desert of emptiness with a few tiny rocks clustered near a dying star in the center. And this desert extends for a mile in every direction. This is our prison. But the Oort Cloud is just the beginning of the problem, because even if we could somehow cross it, even if we build a ship that could travel for 30,000 years through the frozen void, we would still need to reach another star. The nearest star to our Sun is Proxima Centauri. It's 4.24 light-years away. That's about 25 trillion miles, or about 268,000 astronomical units. At Voyager 1's current speed of 38,000 miles per hour, it would take 73,000 years to reach Proxima Centauri. 73,000 years. 73,000 years ago, humans had just begun to leave Africa. We hadn't invented agriculture. We hadn't built cities. We hadn't developed writing. The entire span of recorded human history, from the first civilizations in Mesopotamia to today, is only about 5,000 years. A journey to the nearest star would take 15 times longer than all of human civilization. And Voyager 1 is the fastest thing we've ever built. This is the scale of the problem. This is the true size of our cage. We are trapped not by walls of stone or steel, but by distance itself, by the sheer incomprehensible vastness of empty space. As you lie there, perhaps beginning to feel the gentle pull of sleep, imagine you're drifting through this emptiness, through the cold, silent void beyond Neptune, through the scattered ice of the Oort Cloud. Imagine the darkness, the silence, the absolute, infinite nothing stretching in every direction. This is what lies between us and the stars, and this is just the first barrier. To truly understand the impossibility of interstellar travel, we need to think about these distances not in abstract numbers, but in human terms. Let's imagine a generation ship, a massive spacecraft designed to carry thousands of people on a journey lasting centuries. This ship leaves Earth today, heading for Proxima Centauri at the absolute maximum speed our current technology could theoretically achieve, about 100,000 miles per hour using nuclear propulsion. At this speed, the journey would take approximately 28,000 years. Think about what 28,000 years means. 28,000 years ago, Neanderthals still walked the Earth. The last ice age was just beginning. Humans lived in small nomadic tribes, hunting woolly mammoths with stone-tipped spears. There was no written language, no agriculture, no civilization. The people who would board this generation ship would be separated from the people who would arrive at Proxima Centauri by the same gulf of time that separates us from those Ice Age hunters. They would be a different species, culturally, if not biologically. Everything they knew about Earth would be mythology, ancient history, stories so old that no one could say for certain what was true and what was legend. The stars we see in our night sky are not our destinations. They are our scenery, beautiful, distant, and forever unreachable. The Oort Cloud is the wall of our prison, and it extends for such incomprehensible distances that even our fastest spacecraft would take longer to cross it than human civilization has existed. We are trapped in our solar system not by lack of ambition or technology, but by the fundamental nature of space and time themselves.
So we need to go faster. Much, much faster. If 38,000 miles per hour takes 73,000 years to reach the nearest star, then clearly we need to build ships that can travel at a significant fraction of the speed of light. Light travels at 186,282 miles per second. That's 670 million miles per hour. Even at just 10% of light speed, 67 million miles per hour, we could reach Proxima Centauri in about 42 years. A long journey, but not impossible. A human lifetime. So why don't we just build a ship that can go 10% the speed of light? Because of a little thing called the rocket equation. The rocket equation is a mathematical formula discovered by a Russian scientist named Konstantin Tsiolkovsky in 1897. It's one of the most important and most limiting equations in all of spaceflight. Here's what it tells us. To make a rocket go faster, you need to carry more fuel. But more fuel makes the rocket heavier, and a heavier rocket needs more fuel to accelerate, which makes it heavier, which needs more fuel, which makes it heavier. It's an exponential problem. Let me give you a concrete example. Imagine you want to build a small spacecraft. Let's say it weighs 1,000 kilograms, about the size of a car. Now imagine you want to accelerate this spacecraft to 38,000 miles per hour, the speed of Voyager 1. Using the most efficient chemical rocket fuel we have, you would need approximately 20,000 kilograms of fuel, 20 times more fuel than the weight of the spacecraft. Now let's say you want to go twice as fast, 76,000 miles per hour. You don't need twice as much fuel. You need 400,000 kilograms of fuel, 400 times the weight of the spacecraft. The problem grows exponentially. Chemical rockets, the kind we use for every launch, from the Saturn V to the SpaceX Falcon 9, have a maximum exhaust velocity of about 15,000 miles per hour. This is a fundamental limit based on chemistry. When you burn hydrogen and oxygen together, there's only so much energy released, and that energy determines how fast the exhaust gases shoot out the back of the rocket. And that exhaust velocity determines how much speed you can ultimately achieve. Chemical rockets have already hit their theoretical maximum. We can make them bigger, more efficient, more reliable, but we cannot make them fundamentally faster. To reach even 1% of the speed of light, using chemical rockets about 6.7 million miles per hour, the fuel requirements would be so astronomical that the rocket would have to be larger than the Earth, literally, larger than the Earth. Okay, you might think we need a different kind of propulsion system, nuclear rockets perhaps. Nuclear rockets work by heating hydrogen gas with a nuclear reactor instead of burning chemical fuel. This gives you a higher exhaust velocity, maybe 30,000 to 50,000 miles per hour. That's better than chemical rockets, but not nearly enough. To reach 10% of light speed with a nuclear thermal rocket, you would still need fuel mass millions of times greater than the spacecraft itself. Impossible to build. impossible to launch. What about nuclear pulse propulsion? This is a concept from the 1960s called Project Orion. The idea is to detonate nuclear bombs behind your spacecraft. The shockwave pushes you forward. It's insane, but the physics actually works. Project Orion could theoretically achieve speeds of 30,000 to 60,000 miles per hour, about what Voyager 1 does now. Better than chemical rockets. Still nowhere near light speed, and you'd need to detonate thousands of nuclear bombs to accelerate, then thousands more to slow down when you arrived. The fastest humans have ever traveled was during the Apollo 10 mission in 1969. On their return from the moon, the crew reached 24,791 miles per hour relative to Earth. That's the speed record for human beings, and we set it over 50 years ago. The fastest spacecraft we've ever built is the Parker Solar Probe, launched in 2018. It uses gravity assists, slingshotting around Venus multiple times to build up speed. At its fastest, the Parker Solar Probe reaches 430,000 miles per hour. That's fast, really fast, but still only 0.064% the speed of light. At that speed, reaching Proxima Centauri would still take 6,000 years. Let's say we dream big. Let's say we invent a new kind of propulsion system. Fusion rockets, antimatter engines, something we haven't even imagined yet. Let's say we can reach 10% of light speed. At 10% of light speed, Proxima Centauri is 42 years away. You'd leave Earth as a young adult, you'd arrive as a senior citizen, if you survived. But even that is pure fantasy right now, because we haven't even touched on the energy problem. The amount of energy required to accelerate a spacecraft to 10% of light speed is staggering. Let's use our small 1,000-kilogram spacecraft again. To accelerate it to 10% of light speed would require approximately 450 trillion joules of energy. That's about the same amount of energy as 10 million gallons of gasoline, just to accelerate a single car-sized spacecraft. A realistic interstellar spacecraft would need to be much larger, probably tens of thousands of tons, to carry life support, radiation shielding, fuel for maneuvering, supplies for decades or centuries. The energy requirements scale proportionally. The entire world's energy consumption for 1 year from all sources, coal, oil, natural gas, nuclear, solar, wind, everything, is about 580 million terajoules. To send a single large interstellar spacecraft to 10% light speed would require about 1% of that. 1% of the world's annual energy production. For a single ship. And you'd need that same amount of energy again to slow down when you arrived. Otherwise, you just fly past your destination at 67 million miles per hour, unable to stop. These aren't engineering challenges. These are fundamental physical limits. As you drift deeper into relaxation, your breathing slow and steady, imagine the weight of these numbers. Imagine the impossible energy, the impossible fuel, the impossible speed. We can send robots to Mars. We can land probes on comets. We can even crash a spacecraft into an asteroid to change its orbit. But we cannot escape the tyranny of the rocket equation. Speed itself is a barrier. An impossible wall built from physics and mathematics. But even if we could somehow solve the speed problem, even if we found a way to reach 10% of light speed, we would encounter an even more fundamental barrier: Einstein's theory of relativity. You've probably heard that nothing can travel faster than light. This isn't just a speed limit like the ones on highways. It's a fundamental law of the universe, as unbreakable as the law of gravity. But why? What makes the speed of light so special? The answer lies in the relationship between mass, energy, and velocity. As an object with mass accelerates closer and closer to the speed of light, something strange happens. The object's mass increases, not because it's gaining matter, but because of the energy being pumped into it. At 90% of light speed, an object has more than twice its resting mass. At 99% of light speed, its mass increases by a factor of 7. At 99.9% of light speed, by a factor of 22. As you approach the speed of light, your mass approaches infinity, and to accelerate infinite mass requires infinite energy. The universe simply won't let you reach light speed if you have any mass at all. Only massless.
Let's talk about energy in terms that make the impossibility crystal clear. Imagine you want to send a spacecraft the size of the International Space Station to another star system. The ISS weighs approximately 420,000 kilograms. It's a large structure, but still relatively small for an interstellar vessel that would need to carry everything required for a multi-decade or multi-century journey. Let's say we want to accelerate this spacecraft to just 10% of the speed of light. A modest goal by science fiction standards, but still fast enough to reach Proxima Centauri in 42 years. The kinetic energy required to accelerate 420,000 kilograms to 10% of light speed is approximately 189 quadrillion joules. To put that in perspective, the atomic bomb dropped on Hiroshima released about 63 trillion joules of energy. You would need the energy of 3,000 Hiroshima bombs just to accelerate a single spacecraft to 10% of light speed. And remember, you need that same amount of energy again to slow down when you arrive. So we're talking about 6,000 Hiroshima bombs worth of energy for a single round trip. And that's for a relatively small spacecraft traveling at just 10% of light speed. Where would this energy come from? Let's examine our options. Chemical fuel is out of the question. We've already established that chemical rockets don't have nearly enough energy density. The most powerful chemical reaction we have, hydrogen and oxygen combustion, releases about 142 megajoules per kilogram of fuel. To get 189 quadrillion joules from chemical fuel, you would need 1.3 billion kilograms of fuel. That's 1.3 million metric tons. For comparison, the entire International Space Station weighs 420 metric tons. Your fuel would weigh over 3,000 times more than your spacecraft. And that's not even accounting for the additional fuel you'd need to accelerate all that fuel. The rocket equation strikes again. What about nuclear fission, the same process that powers nuclear reactors and atomic bombs? Nuclear fission is much more energy dense than chemical reactions. Splitting 1 kilogram of uranium-235 releases about 82 trillion joules of energy. That sounds promising. To get our 189 quadrillion joules, we'd only need about 2,300 kilograms of uranium, much more manageable than 1.3 million tons of chemical fuel. But there's a problem. We can't just burn uranium like coal. We need to build a reactor to extract that energy, and that reactor has mass. We need to convert that heat into thrust, which requires more equipment and more mass. We need radiation shielding to protect the crew and the spacecraft systems, which adds even more mass. By the time you account for all the equipment needed to harness nuclear fission, you're back to having a spacecraft that's impossibly heavy. Nuclear fusion might be better. Fusion, the process that powers the sun, releases even more energy than fission. Fusing 1 kilogram of hydrogen into helium releases about 645 trillion joules of energy. That sounds promising. To get our 189 quadrillion joules, we'd only need about 300 kilograms of hydrogen fuel. That's incredibly energy-dense. The problem is that we haven't figured out how to make fusion work efficiently yet. Despite decades of research and billions of dollars invested, we still don't have a functioning fusion reactor that produces more energy than it consumes. Every fusion reactor ever built requires enormous amounts of energy to create the extreme temperatures and pressures needed to make hydrogen atoms fuse. The largest fusion experiment in the world, ITER in France, is expected to finally achieve net positive energy output sometime in the 2030s. But even when it does, it will be a massive facility, not something you can put on a spacecraft. A spacecraft fusion reactor would need to be small, lightweight, efficient, and reliable for decades or centuries. We are nowhere close to that technology. What about antimatter? Antimatter is the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into pure energy, according to Einstein's famous equation, E equals mc squared. 1 kilogram of antimatter reacting with 1 kilogram of regular matter would release about 180 quadrillion joules, almost exactly what we need to accelerate our spacecraft to 10% of light speed. Just 2 kilograms of fuel, 1 kilogram of antimatter, 1 kilogram of regular matter. It sounds like the perfect solution, except for one tiny problem. We can't make antimatter in any meaningful quantities. The total amount of antimatter ever produced by humanity across all particle accelerators and research facilities in history is less than 20 nanograms. That's 20 billionths of a gram. At current production rates, it would take us approximately 100 billion years to produce 1 gram of antimatter. The universe itself is only 13.8 billion years old. Even if we dramatically scaled up our production capabilities, antimatter is phenomenally expensive to create. Current estimates suggest it would cost about $100 trillion to produce a single gram of antimatter. To produce the kilogram we'd need for our spacecraft would cost $100 quadrillion. That's more than 1,000,000 times the entire global GDP. For perspective, the entire wealth of all humans on Earth, every dollar,
Every resource, every asset combined is only about $1.5 quadrillion. You'd need the economic output of Earth for 100,000 years just to fuel a single interstellar spacecraft. And even if we somehow solved the production problem, storing antimatter is nearly impossible. Antimatter cannot touch any regular matter or it instantly annihilates, releasing all its energy in an uncontrolled explosion. You'd need to store it in a perfect vacuum, suspended by magnetic or electric fields, in a container that never fails, never loses power, and never allows even a single atom to touch the antimatter, for decades or centuries, while traveling through the vibrations and impacts of space travel. The engineering challenges are staggering. Let's try a different approach. What if instead of carrying fuel, we gathered it along the way? This is the concept behind the Bussard ramjet, a theoretical spacecraft design proposed in 1960. The idea is that the spacecraft would have a huge magnetic scoop, perhaps thousands of kilometers wide, that would collect hydrogen atoms from interstellar space as it traveled. This hydrogen would then be fused in an onboard reactor, producing thrust. You wouldn't need fuel because you'd be scooping it up as you went. It's an elegant idea. Unfortunately, it doesn't work. Interstellar space is not empty, but it's close. There's about 1 hydrogen atom per cubic centimeter on average. To collect enough hydrogen to fuel a fusion reactor, your magnetic scoop would need to be truly enormous, probably millions of kilometers across. The magnetic fields required to create such a scoop would require more energy than you'd gain from the fusion reactor. Also, as you accelerated faster and faster, the hydrogen atoms you encountered would hit your spacecraft at higher and higher relative velocities. At 10% of light.
Now let's talk about something that science fiction almost always ignores: radiation. Space is trying to kill you, constantly, relentlessly, invisibly. And the faster you go, the deadlier it becomes. If you somehow solved the speed problem and the energy problem, if you built a ship that could actually reach a meaningful fraction of light speed, radiation would kill everyone on board long before they reached their destination. There are 3 main sources of radiation in space: solar radiation, galactic cosmic rays, and at high speeds, the interstellar medium itself becomes a radiation hazard. Let's start with solar radiation. The sun constantly emits a stream of charged particles, mostly protons and electrons, called the solar wind. Here on Earth, we're protected from this radiation by our planet's magnetic field, which deflects these particles around us, creating the beautiful auroras near the poles where some particles spiral down into the atmosphere. In space, without that magnetic field, solar radiation bombards everything. On the International Space Station, astronauts receive about 50 to 2,000 millisieverts of radiation per year, depending on solar activity. For comparison, the average person on Earth receives about 2 to 3 millisieverts per year from natural background sources. A chest X-ray gives you about 0.1 millisieverts. A CT scan might give you 10 millisieverts. Long-term exposure to the levels experienced on the ISS increases cancer risks significantly. NASA has strict career limits on radiation exposure for astronauts. A 6-month stay on the ISS gets you close to those limits. And the ISS is still relatively close to Earth, still within the protective influence of Earth's magnetic field to some degree. Once you leave Earth's neighborhood and head into deep space, radiation exposure increases dramatically. The Moon has no magnetic field and no atmosphere. During the Apollo missions, astronauts were exposed to radiation levels about 5 times higher than on the ISS. But those missions only lasted a few days. A journey to Mars takes about 7 months one way. Astronauts on a Mars mission would be exposed to radiation levels that could cause acute radiation sickness, increase their lifetime cancer risk by several percentage points, potentially cause cataracts, damage their central nervous system, and possibly cause cognitive impairment. And that's just getting to Mars, which is still within our solar system. An interstellar journey would take decades at minimum, more likely centuries. The cumulative radiation exposure would be lethal without serious shielding. So we need to shield our spacecraft. The problem is that effective radiation shielding is heavy, very heavy. The most effective shielding material is hydrogen, because hydrogen atoms are good at absorbing high-energy particles without creating secondary radiation. Water is an excellent shield because it's full of hydrogen. On Earth, nuclear reactor designs often use water as both coolant and radiation shield. To effectively shield a spacecraft from solar radiation, you'd need several meters of water surrounding the entire crew compartment. Let's say you have a relatively small crew module, just 50 cubic meters, about the size of a small apartment. To surround this with a 2-meter thick shell of water would require about 600 cubic meters of water. Water weighs 1 metric ton per cubic meter. So you're adding 600 tons of shielding just to protect a very small living space. And that's only enough to protect against solar radiation. It's not nearly enough for the next threat. Galactic cosmic rays are far more dangerous than solar radiation. These are high-energy particles, mostly protons, accelerated to near light speed by supernova and other violent cosmic events. They come from outside our solar system, from all directions, all the time. They're traveling so fast and carry so much energy that they can pass through meters of solid material. When a cosmic ray strikes atoms in your shielding, it can create a shower of secondary particles that are also harmful. Protecting against galactic cosmic rays requires even more shielding. Some estimates suggest you'd need 5 to 10 meters of water-equivalent shielding to reduce cosmic ray exposure to acceptable levels. A 10-meter thick shell of water around our 50 cubic meter crew module would require approximately 3,800 cubic meters of water, weighing 3,800 metric tons. That's just the shielding, not the spacecraft structure, not the life support systems, not the fuel, not the supplies, not anything else. Just the water to keep the crew from dying of radiation exposure. Remember our energy calculations from earlier? We were trying to accelerate a 420 metric ton spacecraft. Now we need to accelerate one that weighs 10 times more just for basic radiation protection. The energy requirements increase proportionally. We're now talking about needing the energy equivalent of 30,000 Hiroshima bombs. The problem compounds itself. Some people have suggested using the spacecraft's fuel or supplies as radiation shielding. Arrange the water tanks, food storage, and other supplies around the crew compartment to provide protection. This helps, but it only works at the beginning of the journey when your tanks are full. As you consume food and water over months and years, your shielding decreases and your radiation exposure increases. By the time you're halfway through your journey, you might have consumed half your supplies, reducing your shielding by half, doubling your radiation exposure at the point when you're farthest from any help. Others have proposed using electromagnetic fields to deflect charged particles, creating an artificial magnetosphere like Earth's. This is theoretically possible, but the energy requirements are enormous. The magnetic field would need to extend hundreds or thousands of meters from the spacecraft to be effective. Generating and maintaining such a powerful magnetic field would require massive superconducting magnets and enormous amounts of electrical power. And it would only protect against charged particles, not against neutral particles or electromagnetic radiation like gamma rays. But here's where it gets even worse. Everything we've discussed so far assumes you're traveling at relatively slow speeds. Once you start approaching even a small fraction of light speed, a new problem emerges. The interstellar medium itself becomes a radiation source. Interstellar space is not empty. It contains about 1 hydrogen atom per cubic centimeter on average. At low speeds, these atoms are harmless, just drifting past your spacecraft. But at high speeds, these atoms become deadly projectiles. At 10% of light speed, when your spacecraft encounters a stationary hydrogen atom, from your perspective, that atom is hitting you at 10% of light speed. The kinetic energy of that collision is enormous. That single hydrogen atom hits with the energy of a particle in a particle accelerator. It becomes radiation. At 10% of light speed, every hydrogen atom you encounter becomes a high-energy particle that can penetrate your shielding and damage your ship and crew. You're essentially flying into a particle beam. At 50% of light speed, the problem becomes catastrophic. The hydrogen atoms you encounter would hit with so much energy that they'd create showers of secondary particles, including pions and other exotic particles. Your spacecraft would be traveling through what is effectively a continuous nuclear explosion. The shielding required to protect against this would need to be measured in meters of solid lead or steel, not water. We're talking about thousands or tens of thousands of tons of shielding. At 90% of light speed, the energies involved are so extreme that no amount of passive shielding would protect you. The interstellar medium would simply destroy your spacecraft through accumulated damage. This is why science fiction's casual treatment of near-light speed travel is pure fantasy. At the speeds required to make interstellar travel practical, the universe itself becomes your enemy. Every atom of hydrogen becomes a bullet. Every cosmic ray becomes a potential death sentence. Even the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, would blue shift to higher energies and become harmful at extreme relativistic speeds. Some physicists have proposed that a spacecraft traveling at near-light speed would need an expendable shield at its front, essentially a massive block of material that would absorb the impacts and slowly erode away. You'd need to carry enough shielding mass to last the entire journey, knowing that tons of it would be blasted away by impacts with interstellar hydrogen. This adds even...
Let's talk about time. Not in the abstract, relativistic sense we discussed earlier, but in the practical, human sense. Time is the silent killer of interstellar dreams. Even if we solve every other problem, even if we build a ship that can reach a meaningful fraction of light speed, even if we protect the crew from radiation, we cannot escape the tyranny of time. A human life is, on average, about 80 years. That's all the time we get. The longest confirmed human lifespan ever recorded was 122 years. So in the absolute best-case scenario, a human being has 122 years to live, learn, love, work, and experience existence. Now compare that to the timescales required for interstellar travel. Even at 10% of light speed, traveling to Proxima Centauri takes 42 years. That's more than half a human lifetime, just to reach the nearest star. You would need to leave Earth as a young adult, perhaps at age 20, to have any hope of arriving before age 62.
You would spend the prime years of your life confined to a spacecraft, watching the same walls, breathing recycled air, eating stored or synthesized food, never feeling wind, never seeing a sunset, never walking on solid ground. And that's assuming everything goes perfectly. No mechanical failures, no medical emergencies, no psychological breakdowns. 42 years is longer than most marriages last. It's longer than most careers. It's a significant portion of a human lifetime spent in transit just to reach a destination where you might find nothing but a barren rock. But at least at 10% of light speed, the journey is theoretically possible within a single human lifetime. What if we can't achieve those speeds? What if we're limited to more realistic velocities? The New Horizons spacecraft, which flew past Pluto in 2015, is one of the fastest spacecraft ever launched. It left Earth at about 36,000 miles per hour. At that speed, it would take approximately 78,000 years to reach Proxima Centauri. No human lives that long. No human civilization has lasted that long. Agriculture, the foundation of human civilization, was only invented about 10,000 years ago. The journey to Proxima Centauri at achievable speeds would take 8 times longer than the entire history of human agriculture. This is where the concept of generation ships enters the discussion. A generation ship is a spacecraft designed to support multiple generations of humans. The people who leave Earth would not be the people who arrive at the destination. Their children wouldn't arrive either, nor their grandchildren, nor their great-grandchildren. Depending on the speed of the ship, dozens or even hundreds of generations would be born, live, and die aboard the spacecraft before it reached another star. Think about what that means. You would volunteer for a mission, knowing that you will never see the destination. Your children will never see it. Your grandchildren will never see it. You are volunteering to live your entire life inside a metal tube, and you're making that choice not just for yourself, but for your descendants who will have no choice in the matter. You are sentencing dozens of future generations to life imprisonment aboard a spacecraft traveling toward a destination they will only know from stories and images. What kind of life would those future generations have? The ship would need to be enormous to sustain a viable population. Population geneticists estimate you'd need at least 10,000 people to maintain genetic diversity and avoid inbreeding over many generations. Some estimates suggest you'd need 40,000 people to ensure the long-term survival of the population. This means your spacecraft needs to be a flying city with everything a city needs: housing, schools, hospitals, farms, factories, waste treatment, water recycling, power generation, all contained within a closed system traveling through the void. But even a city-sized spacecraft would feel claustrophobic over generations. Imagine being born on such a ship. You've never seen Earth. You've never walked outside without a spacesuit. You've never seen an ocean or a forest or felt rain on your face. The sky above you is a metal ceiling. The ground beneath you is a metal floor. Every breath of air you take has been recycled thousands of times. Every drop of water you drink has passed through the bodies of countless people before you. You learn about Earth in school, see pictures and videos, but Earth is an abstraction. It's a place your great-great-great-great-grandparents came from. It's history, mythology, ancient and distant. What happens to human culture under these conditions? How does language evolve over centuries of isolation? Do the ship's inhabitants even still speak the same language their ancestors did? Historical linguistics tells us that language has changed dramatically over just a few hundred years. Middle English, spoken in the 1300s, is barely comprehensible to modern English speakers. That's only 700 years of evolution. A generation ship traveling for thousands or tens of thousands of years would almost certainly develop its own distinct language, diverging from anything spoken on Earth. What about social structure? Who governs the ship? Do people vote? Is there a captain with absolute authority? What happens when people disagree with the mission? On Earth, if you don't like your government, you can move to another country. If you hate your job, you can quit. If you want a change of scenery, you can travel. On a generation ship, there is nowhere else to go. You cannot leave. You cannot escape. Dissent could become rebellion. Rebellion could become civil war. And a civil war on a spacecraft means everyone dies. History is full of examples of closed communities descending into violence and chaos. The Biosphere 2 experiment in Arizona in the 1990s was an attempt to create a closed ecological system. 8 people lived inside a sealed facility for 2 years. The group split into factions, they fought over food, oxygen levels dropped dangerously low. The experiment had to be ended early. And that was just 8 people for 2 years in a facility on Earth where they could leave in an emergency. Imagine 10,000 people for 500 years with no possibility of outside help. There's also the question of motivation. The first generation who leaves Earth chose to go. They volunteered for the mission. They believed in the dream of reaching another world. But what about the second generation? They didn't choose this. They were born into it. What about the 10th generation? The 50th? The 100th? By the time you're 50 generations removed from Earth, the mission that your ancestors started might seem pointless. Why are we doing this? Why are we suffering in this metal prison to reach a world we'll never see so that our distant descendants might colonize a planet we know nothing about? The sense of purpose could erode over time, replaced by resentment, apathy, or despair. Psychologists call this loss of mission fidelity. Over long periods of time, the original goals of an organization or society can be forgotten, distorted, or abandoned. The generation ship that left Earth as a scientific mission might arrive at its destination as something completely different. Perhaps a rigid theocracy where the mission has become a religious mandate. Perhaps a fractured society of competing factions. Perhaps a dictatorship where mission completion is enforced by violence. Or perhaps the mission is simply forgotten and the descendants live on the ship not because they're traveling to a destination, but because it's the only life they've ever known. The ship becomes not a vessel, but a world unto itself, drifting through space with no purpose beyond survival. There are also profound ethical questions. Is it moral to make decisions that will affect hundreds of generations of people who haven't been born yet and who will have no say in those decisions? We consider it unethical to saddle future generations with excessive debt or environmental damage. But sending people on a multi-generational voyage to another star is far more extreme. You are literally determining the entire scope of existence for thousands of people who don't exist yet. They will never know Earth. They will never have the freedom to choose their own path. Their entire lives are constrained by a decision made by their distant ancestors. Some philosophers argue that generation ships are a form of cosmic tyranny, where the living impose their will on the unborn. Others argue that all parents make choices that affect their children's lives, and a generation ship is simply an extreme version of that. But consider this scenario. 50 years into a 1,000-year journey, we make a breakthrough on Earth. We invent faster than light travel, or we discover that the destination star system is actually uninhabitable and the mission is pointless. Do we send a message to the generation ship? Do we tell them to turn back? And if they're already 50 light years away, it would take 50 years for them to receive the message, and by then, another 50 years have passed. A century would go by before they could even know that everything they're doing is obsolete or pointless.
Now let's talk about one of the most underestimated challenges of interstellar travel: keeping humans alive. Not for days, not for months, but for decades, centuries, or even millennia. Every breath you take, every drop of water you drink, every calorie you consume has to come from somewhere. On Earth, we take life support for granted. The planet provides everything we need. Air is constantly replenished by plants through photosynthesis. Water cycles through evaporation, precipitation, and groundwater. Food grows in soil enriched by billions of years of biological processes. Waste decomposes and returns nutrients to the ecosystem. Earth is a self-regulating, self-sustaining closed-loop system that has been perfecting itself for 4 billion years.
A generation ship would need to replicate this system artificially, in miniature, with zero margin for error for timescales longer than human civilization has ever maintained any technology. Let's start with the most basic requirement: air. Humans need oxygen to breathe. An average person consumes about 550 liters of oxygen per day and produces about 500 liters of carbon dioxide. For a crew of 10,000 people, that's 5.5 million liters of oxygen consumed and 5 million liters of carbon dioxide produced every single day. You cannot simply carry enough oxygen for a multi-century journey. The volume would be enormous, and the mass would be prohibitive. You need a system that continuously recycles carbon dioxide back into oxygen. On the International Space Station, this is done through a combination of chemical processes and electrolysis. Carbon dioxide is removed from the air using chemical scrubbers. Some of it is vented into space. Some of it is broken down through chemical reactions. The oxygen is replenished by splitting water molecules through electrolysis, which requires electricity. This system works for the ISS because the station has a small crew, it's regularly resupplied from Earth, and it doesn't need to be completely self-sufficient. The ISS regularly vents waste gases into space, which is an option only because Earth is nearby and can send more supplies. A generation ship cannot vent anything into space. Every atom is precious. You need to recycle everything. The most efficient way to convert carbon dioxide back into oxygen is through photosynthesis, using plants. It's an elegant, efficient, and self-replicating solution. The problem is that you need a lot of plants. A mature tree produces enough oxygen for about 2 people. So for 10,000 people, you'd need 5,000 trees, plus additional plants for redundancy and to account for plants that die or become diseased. A forest of 5,000 trees requires an enormous amount of space. Even if you use the most efficient vertical farming techniques, stacking plants in layers under artificial lights, you're still talking about acres of growing space. This space requires light, water, soil or growth medium, climate control, and constant maintenance. The lights alone would consume enormous amounts of electricity. LED grow lights have improved efficiency dramatically, but lighting acres of farmland 24 hours a day for centuries would still require a substantial power source, likely a nuclear reactor. And plants are living things. They get diseases. They die. They require constant care. Over centuries, crop failures, blights, and infestations are inevitable. You would need backup systems, redundant growing areas, seed banks, and agricultural expertise passed down through generations. The loss of your oxygen production capacity is an extinction-level event for everyone on the ship. There is no calling for help. There is no resupply mission. If your plants die, you die. Water is another critical resource. An average person needs about 3 liters of drinking water per day. But total water use, including hygiene, cooking, and other needs, is much higher, typically 50 to 100 liters per person per day in modern societies. For 10,000 people, even using conservative estimates of 50 liters per person per day, that's 500,000 liters of water per day, or 500 metric tons. Obviously, you cannot carry enough water for a centuries-long journey. Water must be recycled with near-perfect efficiency. On the ISS, water is recycled from every possible source. Urine, sweat, humidity in the air, even the water vapor in exhaled breath is captured and recycled. The recycling system achieves about 90 to 93% efficiency, which is impressive, but not good enough for a generation ship. At 90% efficiency, you lose 10% of your water with each cycle. For our 10,000-person crew, using 500,000 liters per day, 10% loss means you're losing 50,000 liters per day. Over a year, that's 18 million liters. Over a century, 1.8 billion liters. Where does that water come from? You'd need to carry it all from the beginning, adding enormous mass to your spacecraft.
You need a system that achieves 99.9% or even 99.99% efficiency. Every fraction of a percent matters over centuries. But achieving this high efficiency is extraordinarily difficult. No recycling system is perfect. There are always losses to leaks, imperfect chemical reactions, materials that can't be broken down, and the more efficient you try to make the system, the more energy it consumes, the more complex it becomes, and the more likely it is to fail. Complex systems with many interdependent parts are fragile. When one component fails, it can cascade through the system. Then there's food. Humans need approximately 2,000 to 2,500 calories per day. For 10,000 people, that's 20 to 25 million calories per day. You cannot carry stored food for a multi-century voyage. Food spoils. Even freeze-dried and vacuum-sealed, food degrades over time. You need to grow food continuously. This brings us back to farming. But now, you're not just growing plants for oxygen, you're growing them for nutrition. You need variety. You need proteins, carbohydrates, fats, vitamins, minerals. A balanced human diet requires dozens of different foods. The most efficient approach would be to grow staple crops like wheat, rice, potatoes, and soybeans, supplemented with vegetables and possibly some form of protein like fish or insects, which can be raised in controlled environments more efficiently than cattle or chickens. But this requires agricultural infrastructure. Fields or hydroponics growing systems, lighting, water distribution, nutrient solutions, climate control, harvest equipment, and processing facilities to turn raw crops into edible food. And again, all of this must function perfectly for centuries. Crop failures would be catastrophic. On Earth, if a region experiences a crop failure, food can be imported from elsewhere. On a generation ship, there is nowhere else. A single season of crop failure could lead to starvation. You would need redundant growing areas, diverse crops to spread risk, massive seed banks, and the expertise to adapt to problems as they arise. And remember, this expertise must be passed down through generations. If the agricultural knowledge is lost, if a generation fails to train the next generation properly, food production could collapse. Waste management is another enormous challenge that's rarely discussed. Every person on the ship produces waste. Solid waste, liquid waste, waste from food preparation, waste from manufacturing and maintenance. On Earth, we deal with waste through sewage systems that ultimately discharge into the environment where natural processes break down the waste. In a closed system like a generation ship, there is no away to throw things. Every atom of waste must be processed and returned to the cycle. Human waste contains water, which must be extracted and purified. It contains organic matter, which can be broken down and used as fertilizer for crops. It contains minerals and trace elements that must be recovered. The challenge is doing this efficiently, safely, and sustainably for centuries. Waste processing systems require energy, maintenance, and careful operation. Contamination of the water supply with pathogens from improperly processed waste could cause disease outbreaks. In a closed environment, an infectious disease could spread rapidly through the entire population. Then there's the problem of equipment degradation. Everything wears out eventually. Metal corrodes, seals degrade, electronics fail, mechanical parts wear down. On Earth, we replace things constantly. Your car needs maintenance every few thousand miles. Your home needs repairs every few years. Complex systems like water treatment plants or power plants require constant maintenance and periodic replacement of major components. A generation ship would need to carry spare parts for everything or have the capability to manufacture replacement parts. Manufacturing capability requires raw materials, tools, energy, and skilled workers. You'd need machine shops, fabrication equipment, stockpiles of metals, plastics, ceramics, electronic components. You'd need people trained in every necessary skill: mechanics, electricians, welders, computer technicians, doctors, farmers, teachers. And these skills must be taught to each new generation. If a critical skill is lost because no one trained a replacement, it could.
Let's talk about something that might not seem as immediately threatening as radiation or life support failure, but is perhaps even more psychologically devastating: communication, or rather, the total absence of meaningful communication with anyone outside your spacecraft. As your ship travels deeper into interstellar space, you will experience a form of isolation that no human being has ever experienced before. An isolation so complete, so absolute, that it fundamentally changes what it means to be connected to humanity. Communication travels at the speed of light. Nothing can go faster. This is not a technological limitation, it's a law of physics. Radio waves, which is how we communicate across space, are a form of light. They travel at 186,282 miles per second. That sounds fast, and it is, but space is so vast that even light takes a meaningful amount of time to cross it. Light from the sun takes about 8 minutes to reach Earth. When you look at the sun, you're seeing it as it was 8 minutes ago. Light from Mars takes between 3 and 22 minutes to reach Earth, depending on where Mars and Earth are in their orbits. These delays are annoying, but manageable. The Mars rovers are operated by controllers on Earth who send commands and receive data with a delay of several minutes. You plan your commands carefully, send them, wait for confirmation, adjust. It's slow, but it works. Now consider what happens as you travel to another star system. After 1 year of travel at 10% of light speed, you're 0.1 light years from Earth. A message sent from your ship takes 0.1 years, about 37 days, to reach Earth. Earth's response takes another 37 days to reach you. So any question you ask takes 74 days to get an answer, 2.5 months. After 10 years of travel, you're 1 light year away. A message takes 1 year to reach Earth. The response takes another year. Any communication has a 2-year delay. After 20 years, it's a 4-year delay. After 42 years, when you finally reach Proxima Centauri if you're traveling at 10% of light speed, the communication delay is 8.48 years. Ask a question, wait 8.48 years for the response. By the time you get an answer, the situation that prompted your question has long since passed. You've either solved the problem yourself or everyone involved is dead. This delay makes real-time communication impossible. You cannot have a conversation, you cannot ask for advice and receive a timely answer, you cannot receive emergency instructions. If something goes wrong on your ship, if you encounter a problem you don't know how to solve, Earth cannot help you. By the time your distress signal reaches Earth and they formulate a response and send it back, years will have passed. You will have either fixed the problem or died trying. But it's worse than just delayed communication. As your ship travels farther from Earth, the signal strength of any transmission decreases with the square of the distance. At 1 light year away, a signal is 10,000 times weaker than it would be at 1/100th of a light year. At 4.2 light years, the distance to Proxima Centauri, signals are more than 1.7 million times weaker. To receive these incredibly faint signals, you need enormous antennas and incredibly sensitive receivers. Any interference, any noise in the system can drown out the signal completely. The spacecraft would need a powerful transmitter and a large antenna to send messages back to Earth. The power requirements for transmitting across interstellar distances are substantial, and Earth would need equally large receiving antennas to detect the faint signals. The farther you travel, the more difficult communication becomes until eventually you cross a threshold where communication is no longer practical. You're simply too far away. The signals are too weak. You are alone. Think about what this means psychologically. For the first few years of the journey, you can still exchange messages with Earth. Delayed, yes, but still possible. You can send videos back home. You can receive news from Earth. You can maintain some connection to the world you left behind. But as the years pass and the delays grow longer, this connection attenuates. The Earth you receive news about is increasingly different from the Earth you remember. People you knew have aged, changed, died. Culture has shifted. Language has evolved. The Earth of today is not the Earth you left. After a decade, Earth feels distant and abstract. After 2 decades, it's ancient history. After 3 or 4 decades, assuming you're still alive, Earth is a different world entirely. The children born on Earth the year you left are now middle-aged adults. They've lived their entire life knowing you as a historical curiosity, the people who left on the generation ship. You are not real to them. You are a story, a myth, a footnote in history, and they are strangers to you. Now imagine you're part of the second generation born on the ship. You never saw Earth. Your parents talk about it, show you pictures and videos, but it's not real to you in the way it was to them. And Earth certainly doesn't know you. You are the child of the mission, born in transit, a person who exists in the space between worlds. When you send a message to Earth, if you bothered to, you're sending it to a place you've never been, to people who don't know you exist, and by the time they receive your message, you might be dead of old age. For the 3rd, 4th, 5th generations, Earth becomes mythology. It's the place the ancestors came from, but it might as well be Atlantis or Eden. It's not a real place you can visit. It's an idea, a story, a fading cultural memory. And as each generation passes, the cultural connection weakens. Why would the 20th generation aboard a ship care about Earth? It's hundreds of years in the past, thousands of light years away, completely disconnected from their lives. Earth has forgotten them, and they have no reason to remember Earth. This creates a profound existential crisis. The mission was launched by people who cared about reaching another star, about expanding humanity's presence in the universe. But the people actually making the journey, the ones spending their entire lives aboard the ship, have no connection to that goal. They didn't choose this. They're prisoners of a decision made by their distant ancestors. The destination is equally abstract. Proxima Centauri b is a planet they've never seen, that might not even be habitable, that represents nothing but the end of a journey they never asked to take. The psychological impact of this isolation cannot be overstated. Humans are social creatures. We need connection, community, communication with others. Studies of isolated groups, from Antarctic research stations to submarines, show that isolation causes significant psychological stress even when the isolation is temporary and the group can communicate with the outside world. Total isolation, permanent and complete, with no possibility of rescue or escape, would create psychological conditions unlike anything humanity has ever experienced. There's a concept in psychology called third quarter phenomenon. In isolated groups on long missions, psychological problems peak not at the beginning or end, but around the 3-quarter mark. At the start, people are motivated and optimistic. Toward the end, they can see the finish line and push through, but in the middle, especially around the 3-quarter point, morale collapses. People become depressed, irritable, and prone to conflict. This has been observed in Antarctic winter overcrews, astronauts on long missions, and even sailors on extended voyages. Now imagine a journey lasting not months, but centuries. Where is the 3-quarter point? After 150 years? 200 years? And what happens when that entire generation hits the psychological low point simultaneously? Who helps them through it? Who provides the outside perspective, the encouragement, the hope? There is no mission control to send supportive messages. There is no home to return to. There is only the ship, the void, and the terrible knowledge that this is all there is and all there will ever be for the rest of your life. Some psychologists have suggested that generation ships would need to completely reinvent human society and psychology, create a culture where the journey itself is the purpose, not the destination, where life aboard the ship is seen as meaningful in itself, not as a sacrifice for some distant goal. But can such a culture be designed? Can you engineer human psychology and social structure to make people content living in a metal tube for their entire lives? History suggests that attempts to engineer human society rarely work as planned. There's also the problem of knowledge degradation over time. The generation ship will have a database of human knowledge, technical manuals, scientific papers, cultural works, everything the crew might need. But data storage degrades. Hard drives fail. Cosmic rays can corrupt data. Over centuries, you would...
Now let's address something that might seem obvious, but is actually one of the most troubling aspects of interstellar travel: the destination. Where exactly are you going? And more importantly, what will you find when you get there? We've spent so much time talking about the journey, about the impossibility of crossing interstellar space, that we haven't stopped to ask whether there's anything worth reaching on the other side. The answer is deeply uncertain. Proxima Centauri b is the nearest known exoplanet to Earth, orbiting the nearest star to our Sun. It was discovered in 2016 through careful observation of how Proxima Centauri wobbles due to the gravitational pull of its orbiting planet. We know very little about this world. We know its approximate mass, about 1.3 times Earth's mass. We know its orbital distance, about 0.05 astronomical units from its star, which is much closer than Earth is to the Sun, but Proxima Centauri is a red dwarf star much cooler than our Sun, so this close orbit places the planet in the habitable zone, where liquid water could theoretically exist. And that's almost all we know. We don't know if it has an atmosphere. We don't know if there's water. We don't know if the surface is solid rock or covered in oceans or a toxic wasteland. We don't know if it's tidally locked, with one side always facing the star and the other in eternal darkness. We don't even know for certain that the planet is actually habitable. The habitable zone is just the region where temperatures could allow liquid water. It doesn't guarantee water exists, or that the planet has a breathable atmosphere, or that it's not bombarded with deadly radiation from its star. Red dwarf stars like Proxima Centauri are known for violent stellar flares, sudden eruptions that blast their planets with intense radiation and charged particles. A planet as close to its star as Proxima Centauri b would be subjected to these flares regularly. Without a strong magnetic field to deflect this radiation, the surface could be sterilized, the atmosphere could be stripped away over time, and any life that once existed could be long dead. We simply don't know. And we won't know until we actually go there or develop telescopes powerful enough to analyze the planet's atmosphere in detail, which is decades away at minimum. So imagine you're on a generation ship heading to Proxima Centauri b. You've spent 42 years traveling at 10% of light speed, or more realistically, several centuries at more achievable speeds. Generations of people have lived and died aboard the ship, all with the understanding that their descendants will colonize a new world. And then you arrive. You're in orbit around Proxima Centauri b. Your telescopes and sensors finally get a clear view of the planet, and you discover it's uninhabitable. Maybe there's no atmosphere. Maybe the atmosphere is pure carbon dioxide. Maybe the surface is molten lava from tidal heating. Maybe it's a frozen ice ball. Maybe the radiation from stellar flares has rendered the surface completely sterile. What do you do? You've traveled for centuries or millennia to reach this point. You've used up a significant portion of your ship's resources during the journey. Your population has been confined to the ship for generations. You're exhausted, your systems are degraded, your supplies are running low, and the planet you came to claim is useless. There is no plan B. You cannot simply travel to another star. You don't have the resources, you don't have the fuel, you barely made it here. The nearest other potentially habitable planet might be dozens of light years away. Even if you could restock your ship using resources from the Proxima Centauri system, mining asteroids or moons, the prospect of continuing to another star system is psychologically and practically devastating. Your options are grim. You can try to survive in orbit, living aboard the ship or building space stations, mining the asteroids and moons of the Proxima Centauri system for resources. This might be viable for a while, but it's the same closed system life support problem we discussed earlier, just transferred from a ship to a space station. You're still not on a planet. You're still living in a metal container, breathing recycled air, eating synthesized food. You've traveled across interstellar space to achieve the same existence you had during the journey. What was the point? You could attempt to terraform Proxima Centauri b, assuming it's theoretically possible. Terraforming is the concept of transforming a planet's environment to make it suitable for human life. On Mars, the most commonly discussed terraforming candidate, the process would take centuries or millennia and require technology far beyond our current capabilities. You'd need to thicken the atmosphere, warm the planet, introduce water, create a magnetic field, introduce plant life, create a self-sustaining ecosystem. And that's for Mars, which is relatively close and already somewhat similar to Earth. Terraforming a completely alien planet orbiting a red dwarf star with unknown geology and chemistry could take tens of thousands of years. The generation ship's descendants would live and die for hundreds of generations before the planet became habitable. Again, what was the point? Or you could turn around and go back to Earth. But this is perhaps the cruelest option of all. The journey to Proxima Centauri took decades or centuries. The journey back would take just as long. By the time you return to Earth, hundreds or thousands of years would have passed. The Earth you left no longer exists. The civilization that launched your mission is gone. You would return as ghosts from the past, strangers to a world that has moved on without you. And you would return with nothing to show for the greatest journey in human history, except the knowledge that it was all for nothing. The fundamental problem is that we're making decisions based on incredibly limited information. We can detect exoplanets, which is an amazing achievement, but detecting a planet and knowing whether it's habitable are vastly different things. From 4.2 light-years away, even with our most advanced telescopes, we're essentially guessing. We can measure a planet's size and orbit and make educated guesses about temperature and composition, but we cannot see the surface. We cannot analyze the atmosphere in detail. We cannot detect whether there's water or weather or geological activity. We're betting the lives of thousands of people and the resources of an entire civilization on what amounts to an educated guess. There's a concept in project management called the sunk cost fallacy. It's the tendency to continue investing in a project because you've already invested so much, even when it becomes clear the project will fail. A generation ship traveling to another star is the ultimate sunk cost scenario. After you've traveled for a century, you've invested everything. Turning back seems impossible. Continuing seems like the only option, even if the destination is clearly unsuitable. So, you continue. You arrive, you discover the planet is uninhabitable, and then what? Do you admit defeat? Do you die in orbit? Do you continue to another star knowing the next generation will face the same gamble? This is assuming you can even find habitable planets to aim for. As of now, we've discovered over 5,000 exoplanets. Of those, perhaps a few dozen are considered potentially habitable, meaning they're rocky planets orbiting in the habitable zone of their stars. But potentially habitable is an enormous stretch. It means the planet might have the right temperature for liquid water. That's all. Most of these planets orbit red dwarf stars, which are the most common type of star, but also the most problematic for life due to stellar flares and tidal locking. Many are much larger than Earth, super-Earths with high gravity that would make living on the surface difficult or impossible for humans. Of the potentially habitable exoplanets we found, not one is a perfect Earth analog. Not one is a planet we can look at and say with confidence, yes, humans could live there. The closest we found are planets that might, possibly, under the right conditions, if we're very lucky, be somewhat habitable. That's the best we can do with current detection methods. And these planets are scattered across the galaxy, most of them dozens or hundreds of light years away. Even traveling at 10% of light speed, reaching them would take centuries to millennia. There's also the possibility that we're not alone. We've discussed the Fermi paradox, the question of why we haven't detected any signs of intelligent alien life despite the vastness of the universe. But what if we travel to another star and discover that it's already inhabited? Not necessarily by intelligent life, but by any kind of life. Microbes, plants, simple animals? Do we have the right to colonize a world that already has its own biosphere? Do we risk contaminating an alien ecosystem with Earth life, potentially destroying it? Do we risk bringing alien microbes back to our ship, potentially causing diseases we have no immunity to? The ethical implications of interstellar colonization are staggering. On Earth, colonization has historically.
Given all these insurmountable barriers, physical, biological, psychological, and ethical, is there any hope for humanity to explore beyond our solar system? The answer might be yes, but not in the way science fiction has taught us to imagine. The future of interstellar exploration probably doesn't involve sending humans across the void. It involves sending our creations, our knowledge, and perhaps eventually our consciousness in forms we can barely imagine today. The most realistic near-term approach to interstellar exploration is robotic probes. Machines don't need life support. They don't need food, water, or air. They don't suffer from psychological stress. They can be powered down for decades or centuries and reactivated when needed. They can tolerate radiation levels that would kill a human instantly. They can survive accelerations that would crush a human body. And most importantly, they can be made very small and light, which dramatically reduces the energy requirements for acceleration. The Breakthrough Starshot initiative, announced in 2016, proposes using this approach. The concept is elegant in its simplicity. Build thousands of tiny spacecraft, each weighing only a few grams, about the weight of a butterfly. Each craft would have a small camera, basic sensors, and a radio transmitter. Attach each one to an ultra-thin reflective sail. Then, from Earth, fire an enormously powerful array of ground-based lasers at these sails. The photons from the lasers would push against the sails, accelerating the tiny spacecraft to 20% of the speed of light. At 20% of light speed, these probes could reach Proxima Centauri in about 20 years. They wouldn't slow down, they'd simply fly past at incredible speed, taking pictures and measurements during the brief minutes they're in range, then transmitting the data back to Earth. The data would take another 4.2 years to arrive, so the total mission time from launch to receiving the first images would be about 24 years. Within a human lifetime, we could have actual photographs of another star system taken from close range. This is probably the only realistic interstellar mission we could accomplish with technology that's conceivable in the near future, Not humans traveling between stars, but tiny robotic eyes flying through the void at a fifth of the speed of light, sending back snapshots of alien worlds. It's not as emotionally satisfying as Star Trek's vision of bold explorers setting foot on new planets, but it's achievable, and it would answer fundamental questions about the universe. Are there planets around other stars? Are any of them truly Earth-like? Are there signs of life? The engineering challenges are still immense. The laser array required would need to output about 100 gigawatts of power, roughly the output of 100 nuclear power plants, focused into a beam kilometers wide. The sails would need to be made of materials that can withstand the intense heat of the laser without vaporizing. The tiny spacecraft would need to survive the acceleration, the decades-long journey through interstellar space, and the radiation and impacts with interstellar dust particles. And all of this needs to work autonomously with no possibility of repair or human intervention. But unlike crude interstellar travel, this is at least theoretically possible with foreseeable technology. Another approach that's been seriously discussed is uploading human consciousness into digital form and transmitting it as information. This is highly speculative and ventures into philosophy and questions about the nature of consciousness and identity, but the concept is intriguing. Information can travel at the speed of light. If you could somehow scan a human brain in sufficient detail to capture not just its structure, but its functional state, its memories, personality, consciousness, you could theoretically transmit that information to another star system as a radio signal. At Proxima Centauri, you'd need a receiver and some kind of computational substrate capable of running the uploaded consciousness. Perhaps a future civilization builds automated facilities throughout the galaxy, receivers and computers waiting for uploaded minds to arrive. You transmit yourself as data. 4.2 years later, you wake up in a computer at Proxima Centauri. Your original biological body is still on Earth, or perhaps it was destroyed in the scanning process, depending on the technology. Are you the same person? Is the consciousness that wakes up at Proxima Centauri really you, or is it a copy? These are questions philosophy and neuroscience haven't answered, but from a practical standpoint, transmitting information is far easier than transporting matter. Information has no mass. It requires no life support. It doesn't care about radiation or acceleration. If we could solve the technological and philosophical problems of consciousness uploading, interstellar travel becomes as simple as sending a very large data file. The catch is that this is pure speculation. We don't understand consciousness well enough to know if it can be uploaded, and we certainly don't have the technology to do it, but it's at least theoretically possible in a way that faster-than-light travel is not. We could also send the instructions for building humans rather than sending humans themselves. DNA is information. The entire blueprint for a human being is encoded in about 750 megabytes of data, roughly the size of a CD-ROM. You could transmit human DNA along with instructions for constructing artificial wombs and raising the resulting children to a robotic facility at another star. The robots build the humans, raise them, educate them using transmitted cultural and scientific knowledge from Earth. This creates a human population at another star without requiring anyone to make the journey. Again, this is speculative and raises profound ethical questions, but it's technically more feasible than transporting living humans across light years. All of these alternatives share a common theme. They avoid the impossible problem of keeping fragile biological humans alive during centuries-long journeys through hard vacuum and radiation. They accept the limitations of physics and work within them rather than pretending those limitations don't exist. They're not as romantic as the vision of pioneers boarding a gleaming starship and setting forth to settle new worlds, but they might actually be possible.
This brings us to one of the most profound questions in all of science, the Fermi paradox. In 1950, physicist Enrico Fermi asked a simple question: where is everybody? The universe is approximately 13.8 billion years old. Our galaxy alone contains somewhere between 100 and 400 billion stars. Many of those stars have planets. Some of those planets are likely inhabitable zones. Even if life is rare, the sheer number of possible locations means there should be many civilizations in our galaxy. Some of those civilizations should have arisen billions of years before humans. With that much time, even traveling at a tiny fraction of light speed, a civilization could colonize the entire galaxy. So, where are they? Why haven't we detected any signs of intelligent alien life? Why haven't they visited Earth? Why is the universe so silent? There are many proposed solutions to the Fermi paradox, but one of the most troubling is the Great Filter hypothesis. The idea is that there's some barrier, some filter, that prevents civilizations from spreading across the galaxy. Either life itself is extraordinarily rare, or intelligence is rare, or technological civilization is rare, or something prevents technological civilizations from expanding into space. The filter could be behind us. Perhaps the origin of life is so improbable that Earth is one of the only planets where it happened. Perhaps the evolution of intelligence is a cosmic fluke. If the filter is behind us, we're incredibly special, possibly alone in the universe, and the galaxy is ours to explore if we can overcome the technical challenges. But the filter might be ahead of us. Perhaps every civilization reaches a point where it destroys itself through nuclear war, environmental collapse, artificial intelligence run amok, or some other catastrophe. Perhaps interstellar travel is simply impossible for anyone, not just for humans. Perhaps the barriers we've discussed in this video, the energy requirements, the radiation, the life support challenges, the sheer distance and timescales are universal barriers that no technological advancement can overcome. Perhaps every civilization that looks to the stars realizes, as we're realizing, that the stars are beautiful but unreachable. Perhaps the universe is full of civilizations, all trapped in their home solar systems, all alone, all looking outward and wondering why no one else is out there. If interstellar travel is the great filter, if it's the barrier that no civilization can cross, then the Fermi paradox is solved. The universe is silent because everyone is trapped at home.
This realization that we might be permanently confined to our solar system is initially devastating. For centuries, humans have dreamed of the stars. We've written countless stories about exploring the galaxy, meeting alien civilizations, settling distant worlds. Science fiction promised us a future among the stars. The reality appears to be that we're stuck here, in this tiny corner of space, orbiting this ordinary yellow star, forever separated from the rest of the universe by gulfs of space and time we cannot cross. But perhaps this isn't the tragedy it seems. Perhaps being confined to our solar system isn't a prison sentence. Perhaps it's an invitation to truly appreciate what we have. Our solar system is not small. It's not insignificant. It's vast, beyond human comprehension, and we've barely begun to explore it. We've sent 12 people to the moon, and they only visited a tiny fraction of its surface. We've never sent humans beyond the moon. Mars awaits, an entire world with mountains higher than Everest, canyons deeper than the Grand Canyon, polar ice caps, dust storms that cover the entire planet, ancient river valleys that hint at a time when water flowed freely on the surface. Beyond Mars lie the asteroid belt, millions of rocky and metallic bodies ranging from grains of sand to objects hundreds of kilometers across. containing more raw materials than humanity has used in its entire history. Jupiter's moon Europa probably has a liquid ocean beneath its icy crust, an ocean that might contain more water than all of Earth's oceans combined. Saturn's moon Titan has lakes and rivers of liquid methane, a complex organic chemistry, weather systems, and a thick atmosphere. Enceladus shoots geysers of water into space from an underground ocean. These are entire worlds, each unique, each strange, each waiting to be explored. The outer solar system contains Neptune and Uranus, ice giant planets we visited only once with a single flyby probe. Beyond them lies the Kuiper Belt, a region of icy bodies including Pluto and countless other dwarf planets and comets. And beyond that, the Oort Cloud, extending perhaps a light year from the Sun, a vast reservoir of trillions of comets that we've never even glimpsed directly. Our solar system extends so far that it would take Voyager 1, our fastest spacecraft, 30,000 years to cross it. Humanity could spread throughout this system. We could build cities on Mars, tunnel beneath the ice of Europa, float in the clouds of Venus where temperatures and pressures are surprisingly Earth-like, construct vast rotating habitats in the asteroid belt with artificial gravity and custom-designed environments. We could mine the asteroids for metals, harvest helium-3 from the outer planets for fusion reactors, establish research stations on dozens of moons. We could support a population of trillions living throughout the solar system, each community adapted to its local environment, connected by trade and communication, diverse but united by common origin. This isn't speculation. This is achievable with technology we either have or can reasonably expect to develop in the coming centuries. Traveling within our solar system is hard, but it's not impossible. The distances are measured in light minutes or light hours, not light years. Communication delays are measured in minutes or hours, not years or decades. Resupply missions are difficult but possible. If something goes wrong, help can arrive within months or years, not centuries. Living on Mars or Europa would be challenging and dangerous, but people have always lived in challenging and dangerous environments. Humans live in Antarctica, in deserts, on remote islands at high altitudes. We adapt, we build, we survive. A civilization spread throughout the solar system would be incredibly resilient. A catastrophe on Earth, whether natural or human-caused, wouldn't mean extinction. There would be backup populations on Mars, in orbital habitats, on the moons of Jupiter. Humanity would survive. Our knowledge, our culture, our species would continue. We would have achieved a form of immortality not through interstellar travel, but through diversification within our home system. And perhaps that's enough. Perhaps the meaning of human existence isn't to conquer the galaxy, but to fully explore and appreciate our own cosmic neighborhood. Perhaps the stars aren't destinations. Perhaps they're reminders of the vastness of the universe and our small but precious place within it. Perhaps looking at the stars and knowing we can never reach them teaches us humility, perspective, and gratitude for the one planet we know for certain can support human life, Earth. Because for all our dreams of other worlds, Earth remains unique in all the universe as far as we know. It's the only place where we know for certain that life exists. It's the only place with forests and oceans, with breathable air and comfortable temperatures, with a protective magnetic field and a stable climate. It's the only place where you can walk outside without a spacesuit and not die instantly. It's home, and it's beautiful, and it's fragile.
The same limitations that trap us in our solar system also mean we can never leave Earth behind permanently. No matter how many colonies we build on other worlds, Earth will always be the cradle of humanity, the one place where human biology evolved to fit the environment perfectly. Every other world will require artificial habitats, life support systems, constant technological maintenance. Only Earth sustains us naturally. This makes Earth infinitely precious. We cannot treat it as disposable. We cannot ruin it and simply move to another planet because there is no other planet like it within reach. Perhaps the knowledge that we're trapped here, that this solar system is all we'll ever have, will finally motivate us to take care of what we have, to stop the environmental destruction, to prevent nuclear war, to solve our problems instead of fantasizing about escaping them. The stars are not an escape route. They're a reminder that we're on our own, that this tiny blue world is all we have, and we'd better take care of it. As you lie there, you're breathing slow and deep, perhaps drifting toward sleep. Imagine yourself floating in space, looking back at Earth. A pale blue dot, suspended in a sunbeam, as Carl Sagan described it. Every human who has ever lived, every civilization, every war, every love story, every scientific discovery, every work of art, all of it happened on that tiny speck of light. And unless physics is dramatically different from what we understand, all of future human history will happen within a small bubble around that speck, a bubble measured in light hours, not light years. We are trapped in our solar system by the fundamental laws of physics. The speed of light is not just a speed limit, it's a barrier that divides the universe into the reachable and the unreachable. We can send signals, radio waves carrying information across the cosmos. We might one day send tiny robot probes to take pictures of other worlds, but we cannot send ourselves. The distances are too vast, the energy requirements too extreme, the timescales too long, the dangers too numerous. Interstellar travel, true interstellar travel with living humans aboard ships, traveling to other stars and settling other worlds, is almost certainly impossible. Not difficult, not expensive, impossible. But here's the question that should haunt us as we accept these limitations. If we can't leave our solar system, if the barriers are truly insurmountable, then what about them? What about all the other civilizations that might exist around other stars? Are they trapped too? Is everyone trapped? Is the universe full of intelligent species, all confined to their home systems, all looking outward at the galaxy they can observe but never touch? Or is there something we're missing? Some breakthrough in physics we haven't discovered yet? Some loophole in the laws of the universe that would make the impossible merely difficult? We don't know. We can't know, not yet. All we can say with certainty is that based on our current understanding of physics, interstellar travel appears to be impossible for biological beings like us. But our understanding has been wrong before, and it might be wrong again. So we find ourselves at a crossroads. Do we accept the limitations and focus on exploring and settling our solar system, making the